Okay, so hello everyone. We can start, I think. Today we pleased to have here offline Ari Seitsonen, who is known physicist and chemist, and he is doing band structure calculation. And as I was told, one of the authors of Quantum Espresso. And we actually will do this usual protocol. Time is not limited, and actually your questions also are not limited. But if you see some problems with sound, and just try to give us this feedback immediately. So it is my pleasure to give the floor to Ari.
Well, thank you, Sasha. Thank you for everyone being on site. I know it's hard times for you. Hard times. I'm also thankful that I was given this opportunity to give a talk. First, I start with the apology. So the first one is, as many of you know already, I have this cold. My voice is a bit down. I try to speak loud, clear. And well, if your English is not that good, I try to slow down a bit. So I try to maybe include less of the details of the results. And just I hope that this gives also you some, well, not only many colorful pictures, but also you some understanding. The second apology is that well, I chose this because recently I've been talking also last week in hockey, I was talking about the topic of liquids. So the most of the talk will be on liquids. Only at the end I come to talk about this other topic, two-dimensional material. That's what will be about the defect, the vacancy in graphene. But my background is actually, well, so I'm origin from Finland, from the south between Helsinki and Tampere, almost halfway on the countryside. That's where I grew up, where I went to school. Then also what brings me to Ukraine so often is that this is our home place. This is where also I have one brother, our father was born. So Viborg is there. It was a very important city in Finland. It wasn't even the second biggest city. But, 39 and 1944, the family of our father had to move out because of the war with the eastern neighbor, the Soviet Union at the time. And they settled in this region. Also, the family of our mother is exactly from the same region. That's because they moved the people from the same region to the same region in inner Finland. So they met and said, I have one brother. So we are from this region, but originally our roots are in Karelia, in this part of Karelia, so close to the current border and close to Viborg. But it was countryside. Our grandfather was a farmer, so they gave some land. Our father was the farmer because he was the only son, only surviving son. So those are my roots. Then I studied physics. That's I want to emphasize, even though my affiliation is at chemistry now, I studied physics at the Helsinki University of Technology. It doesn't exist anymore because they merged 3 universities, and then now it's called Aalto University. It's just next to Helsinki, just 500 meters from the border to Helsinki in Espoo. So that's where I got my education in physics. I was doing solid state physics. I studied as a summer student in a laboratory doing a positron physics, experimental. But then soon I switched to calculations, DFT. I think they thought that I'm too dangerous for the equipment. The better give the computers. And so I was studying defects in solids. My master project was about defects, antisides, as on native defects, but antisides, vacancies, and interstitials in indium phosphide, which is very similar to gallium arsenide, 3,5 semiconductor. that was my master's. Then I show more of Europe, just to give you some perspective, and this is also the overview of my what I did in those years after. So my PhD I did in Berlin, Fritz Haber Institute. That's one of the Max Planck Institute, if you know, a big network of institutes. The specialization of this institute has been surfaces. Surfaces, different aspects. I don't remember now exactly how many Nobel Prizes there have been given to this institute, and I'm very proud that I was collaborating with the group leader or two groups in the department of Gerhard Ettel. Gerhard Ettel got the Nobel Prize 2007 for the development of surface science. And since that time, I have been doing surfaces, DFT calculations, mainly on surfaces. I'm not going to talk about them today. I'm sorry, I said I chose the topic of liquids because that's indeed what I have been presenting mostly. But if someone is interested to talk about these surfaces, then I'm here until this evening. So please come and talk to me. Then I moved to Rome. I did 1 year postdoc at the Università La Sapienza. I did then a postdoc next to Munich, Garching. It was actually the supercomputing center of Max Planck Society. It's in the user support, but I was continuing. And I wanted to mention that I already talked with Sasha, that the topic of my PhD was about ruthenium. And during my PhD time, I collaborated, as I said, with people in Gerhard Ettel's department. And they found out that when you put lots of oxygen on the surface, it oxidizes and it forms ruthenium dioxide. And that years calculations ruthenium dioxide. Now it turns out that it's probably an alpha magnet. It's very connected to recent activities also here. So at that time, we didn't know about alpha magnetism, but it sets a small connection also here. So then from Garching next to Munich, I moved to Stuttgart, somewhere there. I was asked to join the group of Michele Parinello. Someone of you has heard about Carr-Parinello method. It's the birth of so-called ab initio molecular dynamics, Parinello methods. So I was first 1 year postdoc in Stuttgart at the Max Planck Institute for Solid-State Research, Festkörperforschung. And then Michele Parinello with, let's say, half of his group moved to south of Switzerland. So I did second year postdoc with Parinello there. Then I was allowed to move and work in Zurich in the group of Hugh Kutter. Hugh Kutter was a former co-worker of Michele Parinello for many, many years. And his best-known contributions to the young generation might be, if you have heard of software called CP2K. So it's about DFT and methods beyond beyond DFT. He's the main author and main driving force of that code. So I was first postdoc with him. Then I got my current position in Paris. I was working at a different university at that time, but since I had liked Zurich, working with Hutter so much, I went back. So I was 4.5 years a research scientist, research engineer, I should say, my position. Then I went back to Zurich on a temporary contract, 4.5 years. And now since 2014, I'm back in Paris. So that's just, I have been going back and forth in Paris. Then if I may mention, my first visit to Ukraine was the conference in Lviv, 2010. And that was my first time after conference. I came to Kyiv for 3 days as a tourist. I came with the night train and flew off. But I remember some sites. Yesterday I had the opportunity with this wonderful sunny weather to go around in Kyiv. So this is my historical background. I mean, you see it's a long way. I left Finland more than 30 years ago. You can guess my age based on that. So several places in Europe where I stayed. And if I could then come back my talk. So I said, I apologize that there will be mostly about liquids. And I studied simulation of molecular dynamics using DFT as a tool to get forces. So ab initio molecular dynamics or DFT-based molecular dynamics when I joined the group of Marinella. So I took this activity or this knowledge a little bit later. And it's also since 20 years that I'm doing molecular dynamics, but mostly in liquids. So then still related to the graphene, we already discussed a little bit. So strong activity for me has been in the last years, the absorption of graphene and very similar material, but which is insulating hexagonal boron nitride on metal supports. This was again a collaboration with experimental groups. I mentioned the collaboration with experimentalists in Berlin, and since then I have been continuing collaborations on surfaces with many groups around Europe. And I had many years of collaboration of this graphene hexagon boron nitride on metal supports. And so this is again 2D materials on surfaces, so interfaces of these materials. And we will see if this collaboration will continue. The good friend of mine, he retired 1 year ago in Zurich. So we see how it goes. Well, that was a long introduction to my scientific background. I said I will mainly talk about liquids and solids. Then the third apology, because I had the flu, I didn't take off this. Well, so my Vishina Banka number 6. I bought it in Kharkiv, and they said it's a bit more modern. I was trying to look yesterday for one from the region of Kiev, but I didn't manage in the short time. Well, I mean, so I'm very honored, happy. I try next time to find a local one. It's from the region of Kiev, because I want to be local, loyal to the local public also. And I have to say, I have now the tradition since let's say 2 years. If I give a talk like this one, where I talk about liquids, most of the topics on liquids are also in collaboration with Thas Brück, who is working in Lead. Some of you might know him. So he's a very world-class specialist on liquids. Yeah. I just to protect my throat there. Sorry, I was planning to keep, not to keep this, but maybe I wrap myself. So he's a specialist in liquids, so-called collective dynamics in liquids, and this will be constitute a major part. And I said the tradition, if I give a talk about the topic, I wear a Vishivanka, one of the first 5, because this is only bought it on Thursday, yes, because give the talk on a Friday, I need it. So I have this tradition of wherever I give a talk, I wear a Vishivanka. So far, I think the furthest distance is last year in Brazil, and 2 years ago in Japan. 10 people sometimes they come and they ask me, where is it coming from? Well, this also, it's not really a Vishivanka, right? But it's also from a shop in Lviv. So finally, I'm coming to start the scientific part of the talk. And this is about liquid water. I mean, the liquid form of ice, of course. And what makes it liquid is that when we heat up ice, at some point, the thermal energy is strong enough that we can break these so-called hydrogen bonds. So hydrogen bonds, people have discussed what is the origin, what is the physics behind hydrogen bonds. In this case, it's of course mostly electrostatic. In the water molecule, oxygen is more electronegative, so it pulls electrons toward itself, and the hydrogens, the protons, are more positive. So there's of course the dipole moment of the water, and there are the kind of two lone pairs of the oxygen atom in the water molecule, and the two positive hydrogens. And when it has a molecule in the neighborhood, well, of course, there's the attraction. So this is what forms the basis of the structure of ice and also liquid water. So we have, on the average, 4 hydrogen bonds, 2 so-called donated hydrogen bonds, where the proton makes a hydrogen bond to the next molecule, 2 accepted hydrogen bonds, where the hydrogens from the neighboring molecules points toward the oxygen of the central molecule. And this is on the average. And the lifetime, so the time that this configuration is, this is kept for a single molecule. Sorry. And not my, this is my cursor, so this is the other computer. Sorry, I just see it. Yeah. Sorry. So the lifetime, so each of these hydrogen bonds on the average in liquid water at room temperature changes once in a picosecond. So this has been discussed on how it happens. So basically, one of the molecules, for example, there's the fifth molecule which approaches from here, and then it's comes closer to the proton than this one, and then this one flies away. So it takes about, on the average, say 1 picosecond to break one hydrogen bond. Of course, the higher the temperature, the faster the hydrogen bonds are broken, because there's more and more thermal energy, the shorter is this lifetime. And now what is interesting, I already mentioned it here. So we were looking, we'll come to this on the next slides, comparing it to the vibration spectroscopy from experiments. Is what is the vibrations of this molecule? This is something that the chemists learned as one of the first examples of normal modes. So the water has 3 normal modes, 2 where the hydrogens oscillate toward the oxygen and again away. This is the symmetric mode, then you have asymmetric mode, and the third one is the so-called bending. So these are the 3 main bands of single oxygen, single water molecule in the vacuum. So then when you have the hydrogen bonds, you can imagine that, okay, we have some bonding here. So it's like, I want to stay in that direction, and I want to stretch a bit longer, this OH bond. And the vibrational frequency of these oscillations is reduced. So the more hydrogen bonds, we expect lower are these OH stretching frequencies. And this is the main target of this first part of my talk.
What is approximately the ratio of frequency of atom for molecule and the distance rise?
So actually, the frequencies. This is now. I don't know if you can see. So this is the vibrational spectra from this OH stretching, and the frequencies are these units in the inverse centimeters, what are often used. It's about well, this is actually so-called heavy.
10 times larger. 10 times larger than molecular.
I mean, this is molecular frequency, but
No,
depending.
10 times smaller. 10 times smaller than molecular.
So
the frequency.
The hydrogen bond. The hydrogen, yeah, it's actually. If this one is, it's almost 4,000 wave numbers, then the hydrogen bonds that the whole molecules move against the hydrogen bond, it's at least 10 times slower. That actually one could see it here one sees vibration, so it's around 500 wave numbers. And in the free molecule, the OH stretching is close to 4,000. So it's indeed close to a factor of 10. So these are then experimental spectra from liquid water. This is Raman spectra at low temperatures. It's a friend of mine, he thanks me now showing these images, Marco Palantoni, so he was the first author. almost 20 years ago, measuring the spectra. This is from the low frequency. So it's known that there are two peaks, very enhanced peaks in Raman spectra at low frequencies. And these are now the molecular modes. They are not the normal modes of the water. What I will be concentrating more in this talk is the OH stretching frequencies. And first, apologies that this is actually too small. You cannot see the scale. And most of the time we are using the so-called heavy water or deuterated water. So instead of having just protons here, we have a deuterium. That's because it helps in our simulations. It reduces the nuclear quantum effects and so on. There are methods like particles we can nowadays easily use to describe nuclear quantum effects of the hydrogens also. I didn't include them here, so I'm mainly working with heavy water. So that's why these stretching frequencies are not close to 4,000. They are rather, I mean, this is 2,500 here. And the different spectra, they are, this is also, this is Raman spectra, two different kind of Raman spectra at different temperatures, going from -10 degrees to 90 degrees. And the experiment is, the spectroscopists often have the bipersonal spectra. This is 2,100, it's 2,900. So the frequency actually increases to what, from right to the, I'm used to the.
What actually, could you say a bit more just pedagogically about this quantum effects of hydrogen? Because what they change in direction?
Well, it's just the effect of the quantum delocalization. It's if you calculate the.
What was the consequences? What you can't calculate? It's like tunneling or.
Well, it's the tunneling is thus. I mean, we have a proton transfer and auto-ionization of water and so on, or the dissociation of water and so on, but it's much slower than no time scale. It's just that for us, in our simulations, it changes the frequencies and so on. Mm-hmm. So if you would include the quantum delocalization to proton, you would change something quantitatively, but not qualitatively. So then if you go to something like order and dissociation of water, so this of course happens in water at room temperature, that the water molecules, they do dissociate. So that's why you have free hydroxyl molecules and then protonated water molecules, because every now and then water molecule.
No, but could you say what it is microscopic properties of water, which fields the quantum behavior and would be different if
So I would say basically qualitatively nothing. Not qualitatively. Quantitatively, yes. There are pictures, I don't have it, but I have seen in reviews, the picture that if we that if we would not have quantum effects, then we would not be alive. Basically, the pH of water would be so different from what it's reality. So that one has to include. And it is about the rate of the outer dissociation of water molecules. So that's really so I could say it's qualitative.
So that's not.
But it is indeed on a macroscopic scale. And it's just because in simulations we can simulate classical nuclei, and in reality, of course, in experiments they always quantum delocalized. And then, as I mentioned, there are ways to describe, and the most famous one to describe the quantum nature of the nuclei, in particular proton, the lowest mass, is the Feynman path integral. So we could do, instead of what I will describe the molecular dynamics, we could use, and many people haven't done it, is to use path integral molecular dynamics.
Yeah, but it is interesting that taking just two protons helps
Yeah. So I mean, one describes all the nuclei with quantum effect.
Proton and you.
Yeah. Yeah. The proton. So yeah, there's lots of literature on this, and then people have shown what are the effects. But I said, to my knowledge, qualitatively there are no errors coming on the microscopes. And these the completely wrong pH. This is known that but this is macroscopic. So I'm concentrating only on small systems.
Thank you.
Yeah, I mean it's very interesting, the nuclear quantum delocalization, because it's not only in this project. I mean also the nuclear quantum effects of hydrogen on surfaces. There are many interesting effects, because when people have shown that you start to delocalize the protons when you had soapten on some surface of platinum. Yeah.
Is it mechanism of molecule dissociation?
That's the outer dissociation. Yeah. So here, I said every now and then, I don't remember the time scale.
Chemical properties. Depends.
So yeah, I'm actually concentrating basically only on physics. So we don't break any chemical bonds. We only break hydrogen bonds here. I would say this is on the side of still liquid physics. It's not chemistry yet, because we don't break any chemical bonds. But the outer dissociation of water, that is then breaking one of these OH bonds. And then, so then the proton goes to a neighboring molecule, then it flies further away, and they're left with a hydroxyl group.
Yeah, interesting. Just of course, I'm very not familiar with water, but I remember this picture from school when we were taught that actually water is not like molecules, but it is separately H and OH and this is H and so on.
Because I mean,
it's far from physical pictures.
Well, the concentration is very low. But of course, everyone, you know that the pH is the definition basically of how much protons and the OH free groups we have. And there was who was it who said that we want pH 0 water, but this would be deadly for us. So this on average, there's always some small, yeah. In my cup of tea, there are, I don't know, billions, which are dissociated on average all the time. Yeah. So such microscope is clear that we don't consider this here. So we want to look only the molecular properties. But I mean, these outer dissociation water, this is one of the examples that are used to then describe chemical reactions in liquid water. And it's easy to calculate, simulate. But in our project, we are not. We didn't do that. It would be interesting to do once we will go into the more delicate projects. The water. So yeah, this was just to show that as a function of temperature, the vibration spectra, I mean the frequency shift, and I'm sorry they didn't have the colors, but the order is here is, you see the first peak is the first spectra here. The highest peak is at -10 degrees Celsius, and the temperature increases toward going down on this side, and here it goes up. So this intensity here grows, here it decreases. And that's because the free molecule, as I mentioned, free symmetric asymmetric ones, the frequencies are somewhere here. So what happens is, because we break the hydrogen bonds, I mean for a short time, but still the higher the temperature, on the average, the more there are free hydrogen molecules with that hydrogen bond. So that's why the intensity here increases, because on the average we have less hydrogen bonds, and without the hydrogen bonds, the frequencies of one molecule are higher. So this is what is kind of clear from the. It's very simple to understand. So then these early experiments, you said this is already very old experiment. What they also tried to do is the dark one is the full spectrum, and then they try to decompose. So they try to understand how much there are, which different hydrogen bond configurations on the average. So they were fitting these full curves with some, I don't know if it's Gaussian or some form, and then they tried to see how many hydrogen bonds there are. And now what we wanted to do is, from our simulations using molecular dynamics, we simulate liquid water at a given configuration, and then we say where the frequencies are. So we know, of course, in the simulation, or we can constrain the hydrogen bonding, and then we can say at which frequencies the vibrations are if we have so and so many hydrogen bonds. So this was the first part of the results which I will show. Then the second part is the so-called collective dynamics, and this corresponds to the phonons in solids. So it's a collective motion, collective vibrational excitations, collective dynamics. It's all the same. So as I said, it's the same thing as phonons in solids. Now it's not so well defined because there are always these molecules also diffusing and so on. But on the average, this corresponds to the same as phonons in solids.
Yeah, but it's like acoustic phonons.
Yeah, this is indeed acoustic mode of the phonons in liquid water. So later I will come to our results, and then I will also show the optical modes in liquid water. So this is a combination of so I again here wanted to start from experiments. There are some classical molecular dynamic simulations also included here. But I just showed that, okay, one motivation was to start from experimental spectra. This is inelastic X-ray scattering spectroscopy. So what one sees is first the elastic peak at the center, and then one sees something on the side. Maybe it's not visible. And these are different momenta of the X-rays. And then when one fits those curves, one finds, okay, there are two bumps always symmetrically around the central peak. And that's actually the inelastic scattering of phonon or collective excitations.
So these two branches are real, right?
Yeah.
So it's not like
no,
one group of people calculate one branch and another.
No, one always has both, because one is absorbing a phonon and the other one is phonon. Sorry, I speak about phonon, but in solids, this would be one side absorbs a phonon and the other one emits a photon.
So does it mean that it has two sound velocities?
Well, no, it's a same. It's symmetric around the center. So here we have only one.
So these velocities can be associated with sound velocity.
They can actually. I'm coming to that. That's also the really interest in our studies. So if we then take the position of these side peaks, and you plot them as in the experiment, you make measurements at the different values of the momentum, the Q. So then you have these dots. This is now inelastic scattering, as it's said there. And this is a good friend of Tarsbrück. So just as these days, they had a common paper of liquid carbon. It is, and this experimenter is working in Rome. He's a professor of physics at the Department of Physics at the Sapienza University in Rome.
It is our Ukrainian journal, Condensed Matter Physics.
Yes.
Journal.
And this is, of course, the connection, because Tals is they're collaborating with Giancarlo. So this is published by the Institute of Condensed Matter Physics in Deep. So this was actually a review article, because the experiments for these, the references here, they come from earlier years. So this was a review of understanding of these effects in liquid water in 2008. I don't know if this was connected to some conference. I know that the channel color has come a couple of times to Lviv. So when one collects, I said the position of this peak, the distance, the momentum, one gets these dots mixed phase scattering in these references. And then there are also dots here. And then we will come to see these are the acoustic modes, and then there's some these acoustic longitudinal mode, and then there's some transverse mode. This is just why there are two branches. So then there's another side peak. I don't know if this no. But well, you see also there's much more scattering here because it's not clear.
But why you put it to 0? Transverse mode could maybe go not to 0.
Yeah, they say that there's a gap. So here, so these are all longitudinal.
I mean,
These
look like optical mode, maybe, no?
It was actually indeed one topic here. They discussed different theories what is going on. Like I understood that, I mean, one theory was that, okay, this mode goes here, and then there's another mode, and then there's this forbidden gap and so on. But they concluded that this is not the correct model. That this is indeed longitudinal, this, and this is transverse, and then there's it stops at some point because they cannot go to 0.
Mhm.
And why there are two slopes? That was what there are some old MD simulations as with classical force field, and my goal was just to reproduce those using DFT methods, and then later this machine learning. So to go going toward smaller values of Q, lower momenta. So you see that most of the points are here, the longitudinal modes, and this is the so-called fast speed of sound, and the high frequency speed of sound. And we know that at the macroscopic scale, so when we send some sound in the water, this is the velocity, this is the so-called adiabatic speed of sound. It would be the propagation of sound in water, because that's macroscopic, so it's very, very close. So that's the slope of this curve.
But this means it has transverse nature.
No, it's the whole project basically is that at the intermediate is basically the intermolecular. If one takes the Fourier transform, this is the intermolecular distance. But when one goes closer and closer to the closer and closer the Q is equal to 0, these points they drop to the lower line. And the transfers they just stop. There's no mode. So I mean, they have marked this probably because they have 2 points. They know that the other one should be. The goal of our study was to follow this transition from this so-called high speed of sound, to close to the high frequency speed of sound, toward the adiabatic speed of sound. You see also in the experiment, so the points start from this line or close to this line, and then they start to approach closer and closer to the slope.
Just a question. In gas, you would have only the upper one, right? In gas, if it's gas and it is evaporated.
Well, do you have any collective?
We have sound and
if it's still condensed, yeah, then I think you would have only the longitudinal one.
So this one due to adhesion, or how it's called, interaction.
How it's called, yeah. And well, there are also 2 modes because we have 2 components, hydrogen and oxygen. So I will come to that.
I mean that in gas there is no transversal component.
Yeah.
Transversal component is absent because you do not have attraction, maybe. Yeah? So you have.
If you have only
repulsion.
Here, just in the materials with very weak interaction. Here we always had the hydrogen bond. So then, if you have water vapor, then what do you see? Well, now I come back to our project. So the goal is to better understand the properties of liquid water. And despite a huge effort, I mean, there are probably tens of thousands, hundreds of thousands of articles in the literature about the liquid properties of liquid water. The people still don't understand everything. And our goal was just to find the model that which would be reliable. And then once we have this model, then we can apply it also to other effects like auto dissociation or then solvation, so putting things in the water. And then also going to the phase diagram of ice. You know, there are at least 17, is it 18, 19 forms of ice. It's amazing thinking that we start from this simple picture, then each molecule is surrounded by 4 hydrogen bonds. Still, you can have 70 different crystalline forms of ice. It's really amazing. So the theory tells that the nature is complicated, even if we start from the single molecule. And in particle, well, here we were interested in collective motions. I said we wanted to start with this. And what we want to do, we want to have this microscopic description. And so I will try to shorten. I mean, I have too much material, but I try to shorten the talk. I will not present everything what I have here. And all the people familiar with molecular dynamics?
Different, more or less, someone experts and another.
Yeah, for those I have just basically 2 slides. What is molecular dynamics? So we try to describe the real dynamics of this atomistic system at real time. I mean, real time means microscopic time also. And we use the Newtonian equation of motion because that works well at the scale of the atoms. And the goal is, if you know the position of atoms in the past, how do we get to the position of the atoms in the future? So what we do is we propagate. Once we know the positions of at least the current positions and maybe some previous position, and then we have to discretize the time. We cannot have continuous time here, so it's because we have to move time step by time step. So the delta D is the so-called time step. So we know the positions at some discrete time just before and now. So how do we get the positions at the next step? We use this molecular dynamics, and that's just propagating the Newton's equation of motion. There are algorithms like velocity Vallée, how to obtain this quantity, the time at the next time step from the previous knowledge of the positions. So in this way, the time increases and we continue to follow the motion of the ions. And then the question is, how do we get the forces on the atoms? The so-called classical force field relies on some parameterized force fields, which have been derived in the past, or you can derive your force field yourself. What we have been using is the so-called ab initio molecular dynamics, where we solve the electron structure problem, so Schrödinger's equation directly at each time step. And this is the ab initio molecular dynamics applied to DFT. We call it DFT-based molecular dynamics. And then the last part, machine learned potential. It's to much extent it's the same as a parameterizing force field. It's in principle same thing. And now we just change the concept because the parameterized force fields, they're usually based on the physics.
But electronic structure, not solids, but molecules. So how it's...
Well, it depends if it's molecular liquid like here, but one can do the same, exactly the same also in solids. So you can parameterize the potential, but then depends if you have a metal. They also parameterize potentials like effective atom methods, effective medium theory. So you have had these models for the interaction. If you have the atoms at this position, what is the force on the atoms?
It's surrounding is important. Right?
Yeah. And the same you could do also machine learning on this. Just that we were here interested in molecular properties. I'm sorry that I don't have really solids. I included the graphene at the end because at least it's halfway. So it's not the molecular liquid, but it's well, can we say two-dimensional solid at finite temperature. So again, this is now relying on so-called data. I'm not going into this in detail, just that we get the interaction between the particles once we have learned these interaction potentials. I said it's similar in spirit here, but whereas here you have usually few parameters which are physically weighted. Here parameters are almost like random numbers. So if you see this potential, it's just a collection of numbers, because these are coefficients in the neural network and this potential. So one doesn't usually include anything about the physics. So you can have completely wrong results if you don't do these parameterization well. So here one has to be careful. So then just giving an idea of the computational cost. So because this is the propagation I mentioned. So you can imagine if I want to discretize the time, delta t, and I have a high oscillations of the atoms in water, the fastest oscillation is this OH stretching. And that time is some femtoseconds. It is like 7-8 femtoseconds. Now we want to discretize that motion. So we have to have the time step which is shorter than this so that we can describe this fast oscillation in that distance. So roughly we can say that we have to have a time step of, let's say, 1 order of magnitude, and the fastest oscillation of the period of the fastest oscillation in the system. And this usually gives half a femtoseconds. It's often used in the literature. So this is when we have these chemical bonds and the liquid water, because we had the OH. Now we had to simulate the real time of the simulation. It's 1 nanosecond, which of course it's nothing compared to the, let's say, biological time or our real Volcook time. We already need to do 2 million steps. And so we need to evaluate the forces on ions. I said only 1 nanosecond of simulation. We have to do 2 million evaluation of forces. And
Is data for machine learning?
yeah, so we can use the data. So if we do this, I said using, for example, DFT. For this time,
Analyze all forces between all
Yeah.
molecules.
yeah. So on each atom we had to calculate the forces at each time step. And so we need here we will need 2 million DFT calculations, and that's doable in small systems.
How many cores?
Yeah, well,
to use?
I mean, the one problem here is, the propagation is sequential. So you had to go to delta t, then you can go to delta 2 times delta t, and so on. You cannot parallelize. In Monte Carlo, you cannot parallelize Monte Carlo, but you cannot parallelize this. So it's one calculation after the other. And well, so for the one set of the simulations I will show, I was only using one old node of our old cluster, but I was running half a year one simulation. It had several nodes, so I had.
And how many cores?
This was only 8 cores. It was old one, but it's also only 128 molecules of water. So the traditional wisdom 10 years ago, people said, okay, we can calculate 100, 200 atoms from DFT. Now it's a couple of thousand if we have a quite big, let's say 500, 1000 cores available for one calculation. So, I mean, I said I was using for most of these calculations some old cluster. In France, we have 3 national supercomputing centers. Each of them has one big supercomputer. We can apply twice a year for grants. And usually nowadays it's easy to get 3 million, 5 million core hours. If one motivates well, one can come to tens of millions. And then in the European project, there was a project called PRAISE. Now it's called, I think, Euro HPC. it's open to everyone, and I think it's also from Ukraine. You are affiliated so that you can apply. And I think the minimum is something like 50 million core hours. 50 million, and you have to consume that in 1 year. So
You call tequilas without beer.
yeah. So these calculations, they become very, very expensive. And again, this is only 1 nanosecond, which is quite short. The simulations I will show, it's hardly 1/10 of this, but it's still then at different temperatures, at different coordinations. It's I said
You mentioned 1 picosecond. It is character time for this molecule. You have to exchange molecules, right?
1 picosecond is for 1 hydrogen bond.
A hydrogen bond.
Yeah. So that's actually a good thing and a bad thing. I will come to that in a moment. This was just about the molecular dynamics in general, what we are doing. If not familiar, I hope I could give you a small explanation. So we want to follow the real dynamics of Newton's dynamics. And we do this by discretizing the time. And then we need, thousands, tens of thousands, millions of time steps to have a reasonable simulation that we can use that. There are methods how to accelerate and effects, but I will not go into that. It's then already a topic for another course or lecture. So just say the beginning of this, I mentioned the Carl-Parry method, so it was 1985. So that was the beginning of this so-called ab initio molecular dynamics. So they were the first ones who combined DFT with finite temperature molecular dynamics. This was the beginning. Now it's more than 40 years since then. And I said that most of the simulations, if we do molecular dynamics with DFT, is using the so-called Born-Oppenheimer molecular dynamics. And that corresponds really that we do one DFT calculation, self-consistent at each time step. We need self-consistent in the Born-Oppenheimer dynamics. So let's say 1 million DFT calculations if you want to do this. And this is what we did. Well, not 1 nanosecond, but still in total we did millions of calculations if we combine all the simulations that we did. So, well, this was just this is all DFT based, no reactions. So it's better also not to complicate. So the only thing what happens here is basically this breaking hydrogen bonds, but there's no breaking of a chemical bond. There are methods to do that, these accelerated schemes. I didn't include any of them. Yeah, the liquid water is something that we can simulate also using classical Hall field, often even more accurately. As I mentioned before, our motivation to find first a reliable molecule with or a model for liquid water, which we can then use in simulations where these classical force fields don't work. Like all the dissociation, they are not dissociable. And then so the first part, the DFT-based molecular dynamics, said molecular dynamics. At each time step, we do a DFT calculation. So this I just want to show the slide at the beginning of DFT. Now, if you are familiar, 1964, the famous Hohenberg-Kohn theorems. Why I'm showing this is because it was actually mostly done at the École Normale Supérieure, where I am now. I'm at the Department of Chemistry, they were at the Department of Physics, but the work, DFT started from the work in Paris at the ENS. And that was, as I said, 1964. The further developments then came from different parts of the world also, when Balticon moved back to USA. But at the time, they were visiting the ENS. Then MLIP, so these are the machine learned interaction potentials. Today we want to avoid the calculus of DFT at each time step using these parameterized potentials, machine learning way of describing the potentials. And then in this study, I will not show results, but this is a PhD students, colleagues, they parameterized one model for water. Then the literature, there are many using these MLIPs. And then later I want to just quickly two two of these. The MACE is probably now the most used model for machine learned interaction potentials. These are all software you can download to start learning your own potentials.
But what is learning procedure based on?
So the roughly what you need is you need first the data. So you need the reference method where you calculate some atomic configurations. You calculate the energy and the forces on the atoms. Then you have many of these, maybe hundreds, thousands. The earlier methods required more, maybe 10,000 configurations. Here, with the latest model, I think I used a little bit less than 1,000 snaps of liquid water. But this is, of course, an easy case because every molecule is more or less the same. If you have something, only one type of ion, you might need more because you have less statistics. Here, all the water molecules are the same. So you need the reference calculations. Then the goal of this software, like MACE, these algorithms, is to learn that if an atom has an environment in the future simulation, similar to what was in the reference configuration, then it would give the forces on the atoms like if the calculation was done with the reference method, like DFT. Again, it's like a force field, classical force field. Now the difference is that we don't have any physical parameters in the potential, just relies on data. We give it so many configurations to the model that it can learn all the parameters.
But how experimental data can be introduced here, no?
Well, it's in principle it could be, but usually it's not because from experiments we have only few numbers like let's say density. I mean density as a function of temperature, the phase space, and so on. But usually we don't use any experimental data.
What is the measure that it is correct potential or not correct?
That's also our goal. So we compare in the experiment, but the result is from the whole simulation. I mean, the first case would be simulate only one molecule of water, so not the liquid, and see what are the frequencies that one gets. Are they close to the really accurate? Because this is, of course, something that sees the measure the very accurately frequencies, vibration frequencies. But what we do is then much more tedious. We do a molecular dynamic simulation, and then at the end we compare the experiments. And one should already warn that, for example, this model, they get very nice vibration spectra, but if one looks carefully, the density of the liquid water is 8% off. So everything looks nice, but the density is wrong. So it's dangerous. And the MP ball, so this is now this potential energy model. This is not machine learning model. It's more a classical force field. It includes two-body, three-body terms, and it has been fitted to some quantum chemistry calculations. So it has only few parameters inside, and it's a classical force field in the well, if I would define it, it's a classical force field, but it's quite heavy to simulate. I did some calculation, and it's maybe 10 times, 100 times slower than.
What means three-body term? So you in previous model it's on the two-body or how?
No, this is a flexible model. So the bond lengths and the angle in the water molecules can change, and it's also adapting to the environment. So it contains the three bodies. So, but usually the MLIP they can go to much higher orders of interaction. It's because you have many more parameters.
No, I mean three body. What is third body?
Well, three bodies. I mean, the classic most used classical force fields, which are much faster than the MP-Pol. They are usually rigid molecule.
Rigid molecule.
Yeah. So then you have only molecule-molecule interaction. Here they include also the three-body term intramolecular.
Intermolecular
Yeah.
interaction.
So this is a bit polarizable and it's flexible. So the classical models that I also still used a lot in simulation, for example, biological systems. They are rigid on the molecules. So there's
So body means internal degrees of freedom.
Yeah. Yeah.
Okay.
And I said that this is the authors, Franz Kopaisson and co-workers, say that these are the most accurate potential. It's more accurate than the other classical force field, like I said, the rigid models and so on. And indeed, the phase diagram is better than in many of the MLIPs. It is much lower than these rigid body models. You can imagine, because you have the intramolecular decrease of freedom in the model, and it's also much lower than the MLIPs. I mean, it's much faster than DFT. But this one, I would say it's DFT based is 1,000 to 10,000 times slower than the classical force fields. And the MLIPs, it's in between. It's maybe 100 times faster than DFT, but still 100 times slower than the classical force field. So why are we interested in this? Well, this is just liquid water. It has two elements, so it's easy to parameterize with potential. But again, this is not dissociable. You cannot dissociate this molecule. Whereas the MLIPs, you can easily include the breaking of the OH bond. So these are much more flexible. You just need more data. And then if you're careful, then this can approach this accuracy. And what has been actually done, there are several works where they fitted MLIP here, and this was called DNN fitted at MP-pol. So they don't take DFT as a reference, they take MP-pol as a reference. And that's because this gives very good agreement with the experiments and large portion of the phase space of water. So ice, different densities, different temperatures of liquid water. So this kind of the reference. And then we fitted also the last one I didn't mention here. The last potential which we fitted is fitted to MP-pol. And then just what I want to come is this model. It's unlike these models, other models, MLIPs here. So usually one just, when one fits, one looks into the close neighborhoods within the central atom. One goes atom by atom, one looks and tries to find the parameters for this atom. So one tries to find the model which reproduces the DFT force inside the sphere. But now one starts to understand that often we need to include also the long distance electrostatic interaction. And the laser was introduced a bit more than 1 year ago. It's called Big summation. And this model which goes beyond these other MLIPs here by including also the charges and thus the electrostatic interaction. And we have now the first goal of this work was we showed that indeed we need to include electrostatics, long distance electrostatics, to have a correct description of many properties of the macroscopic properties. So this I showed already. This is just an technical. So here we use the CB2K. I mentioned Yukuta. It's the main force, the driving force. It's continuously developed. It's free software. One can download it, install, and start running. And the first part we use this so-called GTA function with dispersion correction. And then what is maybe important here is that we restrained this hydrogen bond coordination. At the beginning, I was talking about the different frequencies of different hydrogen bond coordination. So we tried to fix one molecule given configuration. This way we can do simulations which are longer than this 1 picosecond. Because on the average, if we would simulate longer than 1 picosecond, then the hydrogen bond network already changes. And then the spectrum that we would calculate would already contain different coordinations. Here we just fix the coordination, and then this is just the definition for the hydrogen bond that we use. Here's just then some technical details. So what we did, but I will not go in that. Do I have? No, sorry. Then just to mention, so in the DFT-based molecular dynamics, I already said it, we had 128 molecules supported. Now with the MLIPs, we want to go to much bigger systems. That's because when we go to bigger systems in the simulation box, we get to much smaller momenta in the reciprocal space. That's where we saw this transition from high speed of sound toward the adiabatic speed of sound. So we must go to bigger systems in order to be able to obtain the transition. So we cannot do DFT-based molecular dynamics for tens of thousands of molecules of water. That's why we need MLIPs, or we could do the classical models, but we want something for the future. So as a dissociation, polarization automatically, and this is where we have the MLIPs. Then just some definitions. It's because we have two components of the system. So when we fully transform the atomic positions and we take the average, we get the so-called static structure factor, which is S. And this depends on the moment at Q. It's in the reciprocal space. But now because we have hydrogen and oxygen, we can have different linear combinations of these structure factors. And just to show the so-called correlation, concentration structure factor. This calculated as this linear combination of the structure, that's oxygen, hydrogen, and oxygen. This is what we can easily calculate from the simulations because we have the atomic positions for molecular dynamics at this time step, and COCH, they're just the concentrations. So we have 1/3 of the atoms is oxygen, so this is 1/3, and this is 2/3. It's just number the concentration in the system. And then we use the currents. So we take as a current the Fourier transform of the position, the phase factor times the velocity. So this is like a current. So it's a particle current. It's not an electric current. This is just that later we will then Fourier transform these to get the vibrational spectrum. The first part I will go now very quickly because I don't want to bother you too long. This was about these vibrational spectroscopies. We wanted to look at the temperature and the hydrogen bond coordination effects in liquid water. Then we calculated the properties that corresponds to the experimental Raman and infrared spectroscopies. Yeah, I just quickly show some results from the infrared in this article. This also in the Consensus Metaphysics, quite recent. So I only concentrate on the infrared here. So first, this is the number of hydrogen bonds, and 4 is the average, as I said. In in solid ice, the number of hydrogen bonds would always be 4. And now it's only concentrated in the topmost panel because it's just different approximation in the DFT based MD. See the concentrate here. So this was the one exchange correlation combination that we included. So we see that as a function of temperature, when we start from room temperature and we go higher, of course, as expected, as I explained in the beginning, we have less and less hydrogen bonds on average. The number of 4-fold coordinated hydrogen bonds goes down, and we start to have 3-fold, 2-fold hydrogen bond molecules. There's a small minority of 5-fold hydrogen bonded, but this is more or less a consequence of the definition of the hydrogen bond. So we see, okay, we have less hydrogen bonds than the average, as is expected. Then when we look at how that shows up in the spectra, my personal spectra, so in here the dashed line, those are experimental infrared spectra. If you only look again on the top left panel first, so we see that the intensity here goes down. This is at the beginning I saw trauma spectrum, but the same effect is here. So we have a decrease of the intensity at the low frequencies and increase at high frequencies. And I said that the free molecule always stretching is somewhere here. So it's what we expect. We have less hydrogen bonds and the intensity at the high frequencies increases. And then we could derive that.
Could you explain how to imagine what does it mean number of hydrogen bonds? I mean geometrical.
So I mean I showed the picture at the beginning.
Yeah, in the beginning. I
remember. And then here we just defined from the geometry. This is one of the definitions which is often used. So if the oxygen distance between two molecules is less than 3.5, and then if there's a hydrogen in between the two oxygens, I mean, if it's pointing here, then there's no hydrogen bond. But if this angle, I mean, if the two oxygens are here and this is the proton, so if this angle is, sorry, if there's someone online, they don't see. So, yeah, I think it's better.
But what is 5?
So, I mean, if you have a hydrogen bond coordination of 5, then there must be a fifth molecule somewhere.
Fifth molecule.
Yeah. And this has been discussed. I didn't analyze it more.
Nearest neighbors, 5.
Yeah, there's a fifth one in this cell. And we didn't look at it so carefully in this article. I said we see this, but this is actually a very important effect, because this is basically what people say. This is what causes this anomaly of the density in liquid water. And when you start to melt ice, what happens is that it's not that the molecules on average are further away. So there's this fifth neighbor which comes close, central one. And this causes the density to go down. The density goes up. Then there's at the +4 degrees Celsius is the maximum of the density. And then people say that's because, the fifth molecule, it kind of penetrates into the cell. But earlier they were 4.
In ice, it is 4.
It's exactly 4. Yeah. It's they vibrate. Then at some point there's the flip of the hydrogen bond. But then
what means 3? So in ice it is 4, but 3 in liquid it appears as 3 and less.
So I mean it's only on the average.
I understand.
I mean, once the hydrogen bond is formed, broken, then after some time it will find a neighbor and it will bind. So for some time, I didn't estimate that, but for some time it's looking for the neighbor. There's so much thermal energy that it has enough energy to break the hydrogen bond, and it doesn't immediately find another one, but then soon, some maybe hundreds of femtoseconds. And then on the average, takes longer and longer. There are more and more of these effects of breaking the hydrogen bond, and then that's on the average. There's until the water molecule turn away, and there's 1 or 2 hydrogen bonds less than would be the fully coordinated.
So the existence of 5 could be the signature that water could be dense than ice.
Yeah, this is indeed. And I think isn't it this? That's why ice floats on liquid water. So I said that this has been discussed to some extent. What is the nature of this fifth molecule in the neighborhood? I tried to look at it at one point, but then we didn't include it in this manuscript. Where are these fifth molecules?
Once again,
Yeah.
you're telling that the possible reason why the density of liquid water is higher than the ice is because on average in the liquid form there are more neighboring molecules in the coordination sphere.
Yeah, there comes this fifth molecule, which comes. I mean, they also. This is a much more reduced coordination than this one. Still, it's because they are broken on average. But this one, it comes into the coordination cell of the central molecule. So you have more molecules in them. They say that this has been then discussed. So where is this we found? I tried to look at that, but again, the simulations were too short, so it was too noisy, the data. But once you have the simulations, and now if you have a long trajectory, you can analyze where you have the fifth neighbor, which is not along the four expected
So
positions.
just density is not simple average of this.
No,
of
no,
course,
no.
it's some very
Yeah,
complicated function,
cool.
but actually
Cool.
this fifth would play important role.
Yeah, that was has discussed in the literature. And yeah, just to show that sorry, this is way too small. And this is here we have the simulation, different coordinations, and I just want to mention the black one at this lowest one. This is the molecule where you have 0 hydrogen bonds. This is where we said this one molecule is not allowed to have any molecules close by. I mean, there's a numerical noise, but that's basically the somewhere here.
It is absorption. It is absorption.
Well, this corresponds to infrared absorption. Okay. So this is calculated using the dipole moment of that one water molecule. That's the dipole approximation for absorption of light. So this is what we can get from the DFT-based MD. And this actually is something, I think I have it next slide. This is the same thing calculated now with the MLIP. So you see that the peaks are now much narrower here, for example, than here. I mean, here it's only part of the, one direction, part of the frequency scale is reaching, but the peaks are much. Right. That's because we could simulate much longer the MLIPs. Second thing is that here, so this really the dipole approximation, because what we did, it has been implemented also, is that we not only learned machine and potential, we also learned the dipole moment of liquid or aboard the molecule in the liquid. And with that, we can go through then this trajectory from molecular dynamics. Each molecule, we calculate the dipole. When we take the autocorrelation function of the dipole, Fourier transform that, we get the infrared absorption.
Could you briefly explain what group of peaks correspond to what?
Sorry. So I mean, here we have the whole spectrum. So this is just this different coordination of hydrogen bonds. This is actually the same data twice. It's just the different coordinations. And I am sorry that well, it should echo a bit into the details. So I hope I can.
No, but just to say that this central peaks and this left and right, what are they?
Yeah.
How to understand?
So basically, when I have here, so here the top one, the blue one, you see here in the OH stretching. So it has this. Well, there are two frequencies, but what we see basically is one, and that's the pre-OH stretching. I mean, there are two because it's a symmetric, asymmetric, but they appear, they're so close in frequency that it appears almost as if there was one. So these are the OH stretching frequencies. Then when we have the hydrogen bonds donated, then these frequencies shift to this position, you see. And this gives this, then this, if you would take the average of the hydrogen bond coordinations, which I had in the previous slide, I'll show it here. But this distribution of different coordinations, and then you take the corresponding spectra. If you would take the weighted average of these with those configurations found in the water, then you should get the full spectrum. So we have these when we have hydrogen bonds, and when we have no hydrogen bonds, we have this. This is the bending modes. This is for the bending modes of simple or single molecules, and it's not much affected by the hydrogen bond. It changes a little bit, but you see it's not changing much. Then the low spectra, these were the light presence and so on. But this is now you see differences, but this is also related to the fact that we force the molecule to stay in this cage with a given number of hydrogen bonds. So we concentrated in our analysis of this part. I said that these are the OH stretching frequencies. This is the bending, and then these are the molecule against other molecule modes, low frequency ones. And the main effect was just to see that, if we have no hydrogen bonds, we have like a free water molecule frequencies, which is not over. This is of course what we expected. When we have many hydrogen bonds, then the frequencies go down, and then that's also how in experiments the whole spectrum is formed. So it's this whole spectrum here. It's the consequence of these many different configurations. The higher the temperature in experiments or in the simulations, with the short simulations, we have some noise here, but we see this increase in the intensity close to the high frequencies because we have resonance hydrogen. So we have what is expected, and now we have kind of numbers that we have so and so many hydrogen bonds. The frequency changes so and so much from the free water molecule. Then this is just to show this the full spectrum, infrared spectrum. So it's the dashed line is an experiment, and then our simulation gives this line. So the agreement is not perfect, but we are almost there. And we know that using different approximation, the parameterization, we get a more accurate spectra. And if you include the nuclear quantum effects, then we would even closer to the experimental spectra. Now, this was the one part of the results that we got on simulation, and I just quickly show again. This is the case where we have no hydrogen bonds, 0 accepted hydrogen bonds, and the two hydrogens donate 0 hydrogen bonds. So these are the bond lengths, average bond length from the simulation, and the dipole moment on that molecule. And when we go to the truly 4-fold hydrogen bonded molecule, so we see that the more hydrogen bonds, the longer the intramolecular bond. That's because the proton hydrogen feels that, okay, there's something attractive. So the average, it's a bit further away from the oxygen, its own oxygen. And then also the dipole moment increases with the number of and this is something, what is known, that the dipole moment increases from the free water molecule to liquid water. And then also with the case of ice, the dipole moment increases from the free molecule. Then I come to discuss a little bit the collective motions. And this the rest. I try to keep it shorter than the original slides. Again, this was an old study. Again, in the condensed matter physics. Now it's 10 years old. With TARS, we simulated from DFT-based molecular dynamics these collective motions. So what we want to see is this. We'll go very quick. So this was a different momenta in the phase factor. These are just 3 examples, and if we concentrate, sorry, I should see somewhere what is different. Well, if we just take one the left or right panels, I think the right panel was what we want to look at later. To redate this current, which I showed the definition quickly. We again calculate the autocorrelation function, Fourier transform. This is what we would get, and now we can project that to the longitudinal and transverse modes, because we have 2 components. So we have also the optical modes, hydrogen and oxygen. And now if we take the peak of this position, so of the position of these peaks and different wave numbers, or what actually TARS is special, so they fit with the physical form of these spectra, and then they get the peaks even more accurately. One gets the dispersion. So earlier what I showed to you, it was basically this part. And not to such high more. Well, it went quite high at the moment. But again, here we have the only one dash line. This is the high frequency of sound from experiments. Now, there's a way also to calculate this. I don't remember whether we had in the article, but one could calculate also this. And later in Tarsi devised a scheme to calculate the adiabatic speed of sound. So now we could hope soon we can calculate then the adiabatic speed of sound, the second lowest slope. And we see that, okay, this is the lowest K that we can have with 120 molecules. And we are still fully, acoustic mode, we are still fully on the high frequency sound. And that's why we need to go to bigger samples to get transition to closer to the lower slope, if you remember. So the points which you saw before, they are in this regime. So the points should drop well below the dash line here and towards this lower slope that you saw.
But where is experiment? Is
I don't have them in the same slide yet.
Huh?
I don't have the experiment. They were in the.
Actually, it is close to the experiment.
Well, it is close to the experiment, but
I mean, it's easily measurable. Yeah. So.
Yeah, and the data is what I showed at the beginning.
Mm-hmm.
In elastic X-ray scattering and also in elastic meter scattering. Well,
yeah, it's just interesting how far it's from the real experiment.
Yeah, I mean, we could plot them side by side and side. And what we can do hopefully soon is because we get better statistics and I said bigger systems, we can compare also in this region. I mean, now we can compare only here. Then the second part is here we have the optical modes, and we have the longitudinal and the transverse mode. And if you have done calculations or you have seen experiments from ionic crystals, you know that there's a gap, LOTO gap, at gamma point. So gamma point corresponds to K is equal to 0.
Mm-hmm.
So we are just at the part where this start to go to constant. And we can try to estimate the LOTO gap. And then there are some theories which state how long this should be based on the dielectric constants. But again, we were limited here. We estimated, okay, the splitting in the inverse picosecond units. That's what Taras likes. I like the model wave numbers. And this is not too far from the experimental gap. I think we cited the numbers the article. Then I come to show, I hope very quickly, the results from the MLIPs. So again, this was until now it was the results from 2016, DFT-based molecular dynamics. Now we use the MLIPs. And here's just a collection. First, we try to see that we get more or less the correct structure. It's the so-called radial distribution function. So it's the probability of finding this oxygen. So probability of finding at a given distance an oxygen atom if there's an oxygen at the origin. Again, I'm very sorry that you cannot see the units. But the origin, the 0 is here. So the first atom is at origin. What is the probability of finding another oxygen atom? So here we have the characteristic peak, and this is, of course, the hydrogen bond peak. So the average, these 4 nearest neighbors are the characteristic distance, which correspond to this peak. And then those first coordination shell oxygens, they have their hydrogen bonds. And then if you measure the distance on the average from the central molecule to the second, so-called second shell, this gives the second peak, and then it starts to be a constant. And one of these curves, this is again, I'm sorry, the legends. I didn't have time to increase the size. One of the curves here at the bottom is the experiment. It's also not that straightforward from the experiment, to be honest. But there was a long discussion on the experimentist from neutron scattering, X-ray scattering. They were discussing what is the real height of this peak, because it's dependent on how you analyze the data. But the positions are very well given in the experiment, and we see that okay, It's with all of the approximations, it's just the NP pole and then different MLRPs. They give the first peak very well. Then there are some which don't describe this region, and the MLIPs which don't describe this region so well. Here we have deviations. You see, sorry, this is just the same data as here, but just taking the maximum distance is smaller, so we cut this here. So we see bigger deviations with some MLIPs. So we know that on the average, or more or less, water is well described in this microscopic work. Then again, sorry, I just want to show, especially for those, if there's anyone doing molecular dynamic simulations, it's a bit more visible. This is so-called the mean square displacement. So this is on the average how far an atom goes given the time, and it's usually plotted log. And large times this should be linear. This is from motion, and this should go to a constant. And from this, when we fit this slope, we get the diffusion constant. That's the Stokes-Einstein relation. So we can calculate the diffusion constant, and the diffusion constant of liquid water, I don't remember now, it's 0.2 something at these ambient conditions. So we are pretty well describing the NP pole or this ellipse, except the maze. For some reason, I don't understand it's much of a cutoff. Then this actually I didn't include. So the maze laser, this is my own kit. It's also very close to the experiment. These are the good models of liquid water. This was just to convince ourselves that, okay, from these properties, we are close to the experiment. So these are one of the properties that we can very fast evaluate and see if our potential is working well. So with this model, then we went and calculated, then this is the so-called, mentioned earlier, the definition of the concentration structure factor, and this is how it should look like on the log scale. Because analytically it's been shown that this should go in insulators like K-squared. So the points should drop in line. This is the same data as here, but just on the log scale. This is the correlation structure factor. And this is the dispersion. This calculated with these people. Sorry, I didn't go into the larger momenta, but this is now 2000 photomolecules. So the DFT-based MD was 128. Because now we are bigger, we start to see the deviation. I hope, yeah. So this is now the same data as on the previous one, but just showing the smaller range of momenta. We start to see going from the high, the slopes are, by the way, from experiments we haven't calculated also. But at the intermediate, here you see we are on top of high frequency speed of sound, like in the experiment at the beginning. And then now, because we can we have a bigger system, we can calculate the larger K, the lowest K. And we start to see this transition toward this. It was like what we saw in the experiment at the beginning. And then that's thanks to the MLIPs. So we can simulate this is still NP pole. What we want to do is to go beyond this. Here we are at the limit with 2000 molecules of liquid water is slow and slower, even if it's a classical force field. Now with the MLIPs, we want to go even bigger. We want to go to, I already did some simulations of 100,000 molecules of water. I mean, it's nothing compared to the real classical force field. One could nowadays go to maybe hundreds of millions of molecules. But with MLIP, I think with our small machines, we can go to 100,000 water molecules. And then going from 2000 to 100,000, it's cubic, we get, again, smaller and smaller. So I hope to get some points here. But we were stopped for a while. I mean, this is just a collection of the results with people. Because we saw some problems in our simulation, and now I want to make a connection to what I was saying before about this latent level summation, long range interaction. and electrostatics. Because this is something that many people who work in the field of liquid water with these MLIPs don't take into consideration. So these are the two references I gave. This one, this guy, one came January, February last year. Then this was still a reprint. It's the same Beijing and Cheng, and now she's working at the UC Berkeley, California. So this is all about this long-range electrostatics. They introduced the scheme LAs, which is now included in packages like the maze and the lamps, doing molecular dynamics. And what we did was we fitted the potential using this model, and we did molecular dynamics. And what we get is dispersion. Also, we have the LOTO gap. It has some of these points which are not so well converged. I think there's just missing statistics. This was not a very long simulation yet. These again are 2000 molecules, and we have this correct scaling k squared in the structure factor.
But these upper frequencies are observable in experiment. Two upper branches. Optical.
I think these are measurable. I think they have at least in ice, we know, of course, the LOTO gap. In both, I'm not sure actually. I thought it is measurable, but I'm not sure now. So this is now this own model we fitted with LS, and the structure factor. Again, this is the 2000 molecules of water so far. And then this is just to show one of the examples of the MLIPs, which don't include the electrostatics. No longer exposed this. So we see that, we reach kind of the correct value in the structure factor, but then it deviates. They don't drop on a line like here. That's completely wrong. We know that it's unphysical, this one. And because this log scale, there's a region where it looks it's correct, and then it starts to deviate. And the same is in the LOTO gap. It's completely noisy, or it completely disappears. As this corresponds to the same effect that this system, would be, for example, metallic, and it doesn't have a electron gap at all, but it's liquid water. So what is wrong? The same effect. This is just we did the ice at some point. It's the same effect that has been found in the literature. This is now the correlation of dipole in the reciprocal space. So again, as a function of reciprocal distance. So when we go to larger and larger distances, the K decreases, and then we start to see a deviation. So we should have a constant in this dipole. When we go to the momentum zero, that is related to the dielectric constant on the system. But we see this deviation, this zoom, insert this zoom from this region. So we see a deviation. This is the same effect that we see. There's something unphysical happening. And the same dipole at short distance, if one doesn't include the electrostatic, one deviates. Otherwise, one goes to a constant. It doesn't go to zero, it goes to a constant, like here. And the third reference, again, the same effect. One doesn't include electrostatics, and this goes up. It doesn't fully diverge, but it goes to some unphysical value. So what goes wrong? Our understanding is that, the most of the MLIPs I mentioned, they're fitted within this sphere of molecules. So the forces are fitted within the sphere. So the hydrogen bond network is correct. We have more or less these hydrogen bonds, they're all correct. But when we go further and further away, the hydrogen bonds are always correct in the next shell. But the long-range correlation between certain molecule and the further away molecules is lost, which corresponds that we go further and further away, so smaller and smaller k. So the electric field caused by the one molecule, it's still felt far away. And if you don't include the electrostatics, the orientation of the molecules is not correlated, and we get. They still have the hydrogen bomb network correctly, but there's no long-range correlation. Thus, we get the wrong value. Instead of a value which goes to a constant, we have something which goes off. And the range of this, the K where this deviation happens, is practically the same as where we see this deviation here. And I mean, it's related also that it disappears. So this is kind of physically, we had to include the electrostatics to have the water molecules having the right orientation if we go to large distances in liquid water. But this is the message on this part. Then I have a talk way too long. The second part is, as I'm now very much shorter, because this is something I made the results 2 weeks ago. I didn't have time to really think about it and to make further tests. It's just a first analysis of the results. The question was posed. I was attending a conference, actually a so-called physics boat. It's a conference which is held on a ferry from Helsinki to Stockholm and back. And I was there. You can imagine the reason, of course, the nice physics, but also I came to discuss with those people on the boat, and then one has 4 hours to visit the museum or Nobel Museum or whatever, apply for a Nobel Prize in Stockholm at the Nobel Institute. And on that boat, there were some experimentalists who posed the question, so what is the diffusion rate of a single vacancy in graphene? Because they said that in the experiments, which are mostly the tunneling electron microscope images, they say that they see the image of a single vacancy. Now the question is, how fast is the vacancy diffusing? So is it physical that they see it like one spot, or that should it be much faster? Because if the vacancy diffuse much faster, then one should not be able to see it in the imaging. And what we did was just, somehow I zoom. So we did the molecular dynamic simulations using an MLIP. Well, if you are more interested, maybe I show you first the procedure. How I created the MLIP was to run first density function based molecular dynamics of a system of 12 by 12 cells of graphene in a fixed hexagonal box, and then removing one atom, so for the vacancy. So this is 12 plus 12 cells. There are 2 atoms per cell. So is it 288 atoms minus 1, 287 atoms. And then running some tens of per seconds of molecular dynamics at 300, 600, and 900 Kelvin. And then I fitted the potential with this Mace algorithm. No charges here. It's not important. But I had to mention here, we didn't include the spin. So I don't know what is the Curie temperature of a vacancy in graphene, because some people say that it should be spin polarized, at least at 0 K. So I didn't include that in these MD simulations. I did try some tests. I took snapshots and later from this. I calculated spin, and only in one configuration I had the non-zero spin. Is it finite temperature which breaks the symmetry, which removes the spin? Because this might be also effects. You can imagine in graphene the symmetry is high, so maybe the spin is due to some Jahn-Thaler effects and so on, which is then removed at finite temperature. I said that I fitted the potential with Mace. Then I have been doing molecular dynamics at different temperatures. The software I used to do the molecular dynamics, it calls ASC, comes origin from Denmark. I think it's atomistic simulation environment. Now I increase the size of the cell because these simulations are using one so-called GPU for each simulation, and then I still have to run for several days, but I can run nanoseconds. So one GPU, several days, I get nanoseconds of data in this bigger cell. These took several weeks on CPU. nodes which are quite recent, quite big nodes. So I gain a factor of maybe 100 again in speed. So the idea was to do these dynamics. Then I thought, try to show you one of the examples. So this is the system and one configuration. Let's go to the beginning of the. This is the. It's not exactly the beginning of the simulation, but when this that's the starting point. So this 24 times 24 cell. Graphene, every cell has two atoms. It's a honeycomb, as you know. And we are, of course, consider the periodic boundary conditions. So this is like an infinite system. I just showed the simulation cell here. So everything what happens left to this is the same what happens here. And what happens here is just below here also, using the periodic boundary conditions. And then you see at the center, here is now the initial configuration, the vacancies here. Vacancies here, so there's one carbon atom missing. And then launching the molecular dynamics. I think now, when I show like this, I think every step is 1 picosecond, every frame. And it contains 3,000 frames, so it's a 3 nanosecond simulation. Sorry, it's I think I'm sorry, I think it's times 100. No, it's at 300. This was at 1000K. Then you see, I mean, that's because of the visualization. Sometimes there's not really a breaking system.
Is it DFT based or how is?
Not this mix. This is the bigger cell, 24 times 24.
No, I mean it is DFT.
DFT was used as a reference data. Yeah. So again, first
I'm trying to understand. Is it? Do you have some boundary condition for this?
It's periodic boundary conditions. It's periodic boundary conditions. So everything what happens up here happens also below here. But the potential here is the MLIP.
So you do not have some like standing waves here just due to boundary, no. And
I mean, there must be some periodicity because I said it's very. One could try
like
to.
Born karma.
Exactly. Yeah. One should have some. But it is very low frequency.
So it should not fill the age.
Well, it doesn't. I mean, H is periodic, so.
Periodic,
but
anyway.
There's this periodicity. So if you would fully transform this, you would have. You would of course see the.
You will have this frequency. Okay.
Yeah, but it should be very low because 24 times 24 cells.
It's a torus.
Yeah, exactly. So I can't fully transform it, but I believe that those frequencies should be very, very low. And this is anyway, this is a defect. It breaks the symmetry and it has its own factors. This is just you see that sometimes it happens. So now because I'm taking every 10th step here to speed it up.
You mean that actually if you have here the vacancy, it's considered like more superstructure, large superstructure.
Yeah, distance is what is it?
But it is too low.
The distance is certainly too low that it would fill the next one. Yeah.
And if you don't have boundary condition, periodic, you maybe view as vacancy moving to border.
Yeah.
And it modern self-housing of graphene.
Yeah, this could be also simulated. So I mean, what I could do is like the order dissociation is you force one atom away from the lattice set and then it goes on top. And then it would diffuse and maybe after some time it would find a vacancy and heal it. But of course, then it depends how big the system is and temperature and so on. This could be done now, because now the potential, as you see, it's fully reactive. But I fitted it only in the 2D configuration. So if I would put an iPad on, I should fit. Having this different kind of coordination. One warning is here. So I mentioned this 1000K, but in the reference data I have only 900K. So I'm on a dangerous zone. So because again the MLIP doesn't know anything about physics, so should be very careful not to go to much higher temperatures than where I was taking the reference data. But so you see that it's fluctuating. Of course, this is like a random motion. It's not that it diffuses always direction.
It's like brown in motion, but
Yeah.
could you apply some gradient, I don't know, temperature gradient or some gradient
Yeah.
to see its motion?
Yeah. But good. I mean, one simple case would, because again, now I took a hexagonal cell and I could take a rectangular. The distance between the vacancies would be so big that it would not affect. What I could do, for example, is to give that, okay, the range of these atoms have some temperature, and then some atoms below or far away would have some. It's like a non-equilibrium molecular dynamics. So people calculate like conductivity, like having two different potentials, small difference, different regions, and then look how, for example, ions fuse. So here one could do the same, have on the average some driving force from one part to another part. Then it would be kind of directed dynamics. So
yeah, from here you can estimate some characteristic time.
Yeah.
This,
so
actual diffusion rate. It's
well, I tried to do it, but how accurate that is? Again, I just collected the results very recently.
Hello, may I ask a question?
Yeah.
I'm also dealing with graphene and graphene quantum dots, and also I'm using machine learning potential, and I have some issue with calculation of formation energy for vacancy. Yeah, because it's a huge gap between what DFT gives me and what LEAP gives me. How do you figure out this issue maybe? And other issue I have, it's related to infinite graphene and finite graphene quantum dots. Because formation energy it depends on coordination sphere. I mean how what distance from the center to the edge of quantum dot, and this depends the difference for DFT calculations and for LEAP calculations. So maybe you met this obstacle, and which models did you use? Maybe you did some fine tuning. Because I tried ORB, then 7net also. At the beginning of this year, they released a new model. And yeah, so maybe you give me some insights.
So first of all, the model I didn't mention. Sorry. So in the model, in the DFT molecular dynamics, I used PBE as the exchange correlation approximation, the exchange correlation term. So it's a GGA, because we know that in solids it works more or less fine. What we could do now is, because for the machine learning we don't need to have really molecular dynamics, is to calculate some snapshots with a method which is slower, like hybrid functionals, and then we could compare, say, using a HSC06 hybrid functional or screened hybrid functional and PB, and then looking if we have a big difference. Of course, this is not to prove that the potential is good or the reference is good, but at least we maybe get more convinced if two different functions give more or less the same results, that our potential is quite accurate. So this is something to be done. Then about the quantum dots, well, I'm sure that's much more complicated problem also because you have I know how you saturate edges of the of the particles here because we have periodic boundary condition. And on average, we have always a coordination of 3, except in around the vacancy. So it's much easier than I think what you are fitting.
Yeah, much
So what
easier.
we,
Yeah.
yeah. So what and because then still about the model maze, when I basically used very good convergence parameters, a large radius for this learning and very large network, because I thought, okay, it's only one element and I can go. The potential is maybe slower, but I hope it's more accurate also. So I tuned the parameters so that they are more reliable. And because again, there are only 2 types of carbons. There are only carbons and only 2 types, sp2 or then at the vacancy. So I think my problem is much easier than yours. So I'm not saying that you should give up, but just that my case was quite simple compared to what you are doing. So
Yeah, thanks.
yeah, I mean, if you want, we can discuss later more. So now coming also to Chester was asking, so here's the combined results. I estimate the frequency of jumps now how many jumps there are per picosecond at different temperatures. I must admit that probably due to the poor statistics, the point at 300K doesn't really fit the results. But and you see some fluctuation, and I think this all the simulation have to be longer. So I'm thinking of still fitting a new potential and then repeating all this exercise. This was just to get the first idea. So then if we invert, so we just take 1 over the frequency, we get the characteristic time. So the average time before the jumps or the diffusion of the vacancy. This is again as a function of temperature, and of course, the higher the temperature, the faster the vacancy moves. So the smaller this characteristic time between the average time between the jumps. And last, my hope, eventual hope was to try to get the diffusion barrier. This, of course, assuming that it's Arrhenius-like behavior. I must admit, so I did as a visualization I showed was 1000 point at 1100 is off the line, 1200 again on the line, and then 300K I mentioned it doesn't really fit this. So again, I want to improve the line. If it turns out that the for example at the 300K the trend is not the same, so that it's not close to this fit. It might be that there's a different mechanism for the.
Because this is far from quantum fluctuations.
Yeah. So then it's maybe something else which only appears at low temperature when you out temperature. So that's still to be determined. But of course, the lower the temperature, the longer I had to simulate to get the average time between the jumps of the vacancy, and maybe it was not still enough. These longer simulations are 12 nanoseconds. And then I'm afraid that was it that at 400K, for example, I have only less than 10 events of diffusion. So 300, I still would have to simulate maybe 10 times longer. And probably I still try to find or fit a more accurate potential and consider all the effects. So this was just the first shot. I was happy that at least more or less I aligned when I hit these points. So sorry, you don't see at the unit at the bottom is the inverse temperature. Inverse temperature, because this is the Arrhenius form. So you have the rate is the prefactor times e to the area divided by kbt. So the dependence should be exponential in 1 over t. So when we plot this on the y-axis and logarithm axis, points, if it was used like give a straight line. It seems that it's fitting, and the conclusion from here would be here the 300k, so it would be somewhere here. The diffusion, the jump rate would maybe be something like 1 every nanosecond. So that would be just if I look at the line, or maybe even lower. The diffusion rate, if the imaging rate in the experiment is 1 second, certainly the diffusing according to this simulation will diffuse much faster. If the measurement rate is a nanosecond, then it's just at the scale of this. If they would do it with STM at room temperature, the vacancy according to my simulation would diffuse much faster than what they scan STM.
You know, it may be a bit similar in vortex dynamics in superconductors, vortex lattice, vortex dynamics. There is flux creep, which is maybe similar to this, but also there is such a regime which is called servo assisted flux flow. It is when you take into account one there and back, jumping there and back, you have something like linear behavior.
Yeah.
Maybe it has some similarity.
Yeah. Also, to be honest, so I was only looking at all the to get these values. I was only looking at changes in position. It could be that it goes back. It just make a quick jump and goes back.
It relates to that question which I asked about some driving force, because here is some accidental, but if you have some macroscopic driving force, you can feel this effect that somehow not correlation, but something different. Because here you do not have you do not have some macroscopic force.
It is pure random motion. Well, it's all what I wanted to tell you today. I'm sorry that I gave very long. I mean, just to give a second part was to give you an idea. Okay, like can be used in this kind of simulation. These are all molecular dynamics. And one of the reasons earlier I said, well, here the time step was 1 femtosecond. So to get 1 nanosecond, again, 1 million simulations. Now it's just much faster.
Okay.
Maybe a couple of days on a GPU.
Good.
And many atoms.
Okay, let's thank the speakers then. This time and actually the questions. So maybe in addition to the long, we can discuss questions from the online audience or from offline. I had actually a general question about this water dynamics and water. You said it is many questions are not clear. Could you mentioned briefly what could you somehow give examples of actually the most interesting unclear questions of this is what the dynamics and what the properties of.
Well, single properties, I mean, people discuss then what is the origin, for example, the density, the maximum density. Why is it at 4 degrees Celsius? Maximum of the density.
So it is still.
Well, there are different suggestions, but then I don't know if there's any convincing model. Why is it just at 4? Why it's not the 0K or?
So there is no single widely accepted model which reproduces this result.
I haven't followed if well, for example, the phase diagram is quite well reproduced by the same people, but it doesn't relate to.
Is this 15 phases or 7?
That's ice, yeah. And then what people usually do when they do liquid water is they show the density as a function of temperature. And the best models, well, they get always the maximum, but as I said, the DFT-based MLIPs, the LDFT, if one could afford to do it, the density is 8% of 6%, 8. Then if one takes a different model, one gets closer, but just taking something what we consider as reliable, it's not very good. And then just to say, what is the challenge? So people have collected, and I don't remember what is the number. There are at least 20 anomalies in liquid water, which are not typical for simple liquid, let's say argon or so. So they're not only the density, the maximum density, there are many which behave unexpected. And I don't know if any of the model, how many could they locate, let's say, at least relatively accurately. So this just shows we have a simple liquid in principle, only hydrogen bonds on the average 4, but it gives many strange behavior. So then to understand all of these and what is the origin and another.
Could you name another chemical molecule? What is substance which is similar to water?
So actually,
properties.
Actually, one property, I didn't mention this, but what has been discussed a long time is whether there's a liquid-liquid phase transition. And now people say that there's one, it's in supercooled water, and it's in a region which people usually call no man's land. In principle, you can never reach, maybe one day, because it's at such low temperature that if you do experiments, the water freezes too fast, even if you have ultra-pure water. I mean, that's the way they expect there to be a liquid-liquid phase transition. That's again critical point. In addition to the normal one. And then there has been suggestions that other liquids might have that. And if I'm not wrong, liquid silicon is also expected to have a critical point. There are some examples.
Single molecule or total?
I mean, just liquid silicon, so one. There are other examples where they expect to have a liquid phase transition second critical point. So it might be that there are some examples. I don't have others now in head, but there are examples where we have things. But certainly, water is the one which, as I said, more than 10 weird properties. And if we think that we have only hydrogen bonds, so
what is so special about hydrogen bond?
Why it's relatively weak, and I mean, in principle, it's quite directional, right? So, I mean, to be honest, when you go, for example, this why there are so many different forms of ice. So we come back to the nuclear quantum effects. It has been shown that in some actually the proton quantum delocalized between two oxygens. So when you go to low temperatures, it's high pressure. So it's not that we have always the same molecule, like simple molecule, but you start to give away one proton to the neighbor and the other one.
Does it mean water has a simpler phase diagram? In the sense that in heavy water, does it have a simpler phase diagram? Because the localization effects are much weaker.
It just shifts to different part of the temperature, pressure phase. I haven't fully followed it when it has been all measured, the full, because still the latest edition was it ice. So they have something like, when was it, 5 years ago, 10 years ago, They had 15 crystalline phases, and then they had high density amorphous ice. They had low density amorphous ice, and I think they have even very low high density, very high or very low density amorphous form. And I think they might have added in the last 10 years 16th, maybe even 17th form. So I said, it's still discovered the full phase space. Of course, we are going to an exotic, very rare process, or maybe you might have metastable phases also, but they're really more than 15 crystalline phases, and start saying that okay, it's a simple molecule with electrons. But again, there's the nuclear quantum delocalization coming into play and so on. So that's changing, making it more complicated. So liquid water itself, there's this liquid phase transition. Then there's still 3 years ago, new papers saying that okay, we measured that there are not two phases of water, and there has been modeled that his fifth neighbor is because we have kind of two different forms, high density, low density phase, and then they are averaged in the liquid water. And 2-3 years ago, there was a Chinese group who suggested there's also a third kind of water. So it's all still unresolved, and I said simple liquid water. Just to understand, I mean, we understand the properties, but again, there are some effects that, of course, as physicists, we want to understand the origin, where it's come from. But we are not there yet.
Maybe more questions?
Yeah.
If I understand, you use DFT at each step of molecular dynamics to determine potential.
Yeah, all the forces.
Can we reformulate this problem as like mean field problem? We have a data of potential who depends on temperature and disordering in system. Not by water, maybe for disordered crystal. Can we determine new pseudo potential who depends on temperature and disorder?
I could imagine that this can be done, and probably the way would be machine learning, not in the way like I have shown here, that we then do a microscopic model of water, but maybe we can then fit not the atomic position coordinates, but to say temperatures and so on, and then we could predict the same at different temperatures. And this is the different way of artificial intelligence. So I'm only fitting a potential, atomistic potential, but of course, machine or artificial intelligence is much also. We take more macroscopic properties, like you say, and we don't describe the system anymore atomistically, but big properties like temperature, pressure, then some properties like local dipole moment and so on.
It may be a way to introduce in DFT CPA coherent potential approximation, or self energy of one interaction. So
And I mean, then to say about DFT and machine learning, there are people who are trying to find the ultimate exchange correlation function using machine learning. So I haven't followed how they do it, but I mean, it kind of shows that okay, people have given up finding the exact analytic form, which might be, of course, horribly complicated. but trying to find a functional form which would work best in most simulations. Whether that would include then better effects like self energies and so on to get, or I mean, of course, if we had the exact functional, it should give us correct properties. Well, bandgap, I'm not sure. It might be that even exact function doesn't yield it, but the hope is that maybe machine learning gives us not only a better post fields, it also eventually gives us the ultimate or better and better exchange correlation functions. I think in the next couple of years we see people make progress in this direction. Now people do, it's just they calculate some properties, compare with experiments, and try to find a better parameterization. Maybe machine learning can give us even better approximations. So, and then we don't need any more to do tricks like plus U, or it would be automatic.
Okay. I think we should finish this soon. Any questions? Still, okay.
When you say about GFT calculation, you perform this calculation at 0 temperature, yes?
The electronic temperature.
Yeah. Okay, and then you say about DFT-based MD calculation.
Yeah.
What about justification, validation to use potential parameters which are validated ground temperature in the case when the temperature is much higher?
Yeah. So I take I start with the case of water. So what we assume is this von Oppenheimer molecular dynamics, and this basically states that the electrons stay always at the ground state, and when the gap is like in liquid water, I think it's 8 electron volts. So there are no thermal excitations. So this saves us in the case of liquid water. So because the band gap is so large, there's no thermal excitation of the electrons through the gap. So that's why the 0K DFT is fine. There are extensions of DFT to finite temperature. Then in the second case, of course, the second system I discussed at the end, graphene. So here the system is metallic. Graphene itself is a semi-metal, and here we use a trick is a Mean-field trick of broadening of the occupation numbers. We don't do real dynamics of the electrons, but on the average, we treat the Fermi-Dirac distribution of the electrons. So this is, I think, a good approximation usually, even if we are at a high temperature like 1000 K. So it is a mean field approximation to the real electronic excitations. Sparing, yeah. Fraction occupation numbers, mirroring, broadening, these are the same thing. But it's really a mean field approximation. Again, we are not really exciting any electrons. It's just on the average how it would behave. I think on the scale of the other errors that we have, we believe that this minor error. We would be on the scale of very fine details of the electron structure. This would be a huge approximation. But again, we believe that if we make an error there of some millielectron volts, and well, sorry, I don't have the estimation for the gap. Sorry, the barrier here, but of course it's several electron volts, the diffusing barrier. So then if we make an error of some millielectron volts, this midfield occupation numbers broadening, I think we can leave it, but it's an approximation. Again, in this system, when we are high temperature, we believe that we can wipe out
these numbers, these parameters of simulation, like 1000 Kelvin or 400 Kelvin. Are those temperatures the electronic temperature or somehow the approximated real temperature?
This is the ionic temperature.
Yeah.
And now that, of course, that's actually a good point relating to the last two questions. So when we do the bitten here, I mean, this learning of the potential, we have the forces here, and they're calculated. If I calculate 300, and if I use the broadening occupation numbers at 300K, I use the same 600, 900K. I mean, it's not very probable, but what could happen exact the same atomic positions, but the forces are slightly different because the broadening is slightly different, right? So if I use a different broadening 300K for the electrons here, then it's not consistent because this model doesn't know at which time it's. So it is an approximation then to the occupation number. So it's a kind of a midfield. But again, I believe that this broadening error is, the code tells what is the energy into the broadening approximating. So I'm going to check, and I guess that this is much, much lower than the ionic kinetic energy. I again hope that this is a minor approximation. It's there. It's the same as I mentioned. I don't know what would be the Curie temperature of the vacancy, but it might be that 0K, probably the temperature. The system would be magnetic. If I just relax, then that's probably until. And I didn't mention that to the dynamics. There's some discussion that at very low temperature, like plus STM, a few Kelvin, the vacancy is certainly localized. But there are some people, I mean, a colleague of mine told that they say that there's a distortion, probably Antella, and then it's probably magnetic. Though this is non-magnetic. So this will be another factor that if it fits at very low temperatures and it's magnetic, then you have to tell this procedure that okay, there's not only the forces of the atomic positions, but there's also the magnetic moment that one should put in the fitting. I try to wipe all this out. So I hope that the high temperatures, these effects go away. But I said, it might be that in the future we have to go to the, maybe it's not seen here. Sorry if I'm speaking too way too long. Is that, for example, here you see a configuration of the vehicles where this distance is much shorter. These two are longer. You see, these two distances around the vacancy are much longer. And this is much shorter. So this is, of course, fluctuating. And it might be that at very low temperature, this freezes. So that there's the Jantelle distortion, and this would be the ground state, the very low temperature. And we fit that again, the very low temperature, it's magnetic. So the next goal is still very low temperature when we have the molecular dynamics. I mean, there's no diffusion. Oh, it's so slow that we don't see it. But then we want to look at, if we concentrate here, sorry, anytime just talking. Now I slow down it a bit. I slow down a bit. So if we would look at the statistics at the low temperature, how long is one short? Too long, and then it would turn. So if it's very slow, then in experimental STM, you might be able to see one. Then later, hours later, maybe it's in different orientation. It's not diffusion, but it's another barrier. Like I said, it's just the barrier to rotate kind of the two bonds within that.
What was and maybe is your main motivation to study PIs in practical application?
Well, it's eventually we want to do a solvation, so put something into liquid water. First, my goal is supposed to have the best model, which was describe most of the properties well, and then to go, for example, isotope effects. I mean, I mentioned the deuterated water and the normal water where we have proton instead of deuterium. And if you want to have these differences, heavy water or even isotope mixtures, then what is the best model to describe both? And then we go beyond water to different molecules and understand what are the kind of characteristic, also how to do the fitting MLIPs. But the water is just it's a eternal swamp, so there remains always something to be discovered. So there still appear papers about just pure water every now and then. The recent years it was so much about these nuclear quantum effects also. Now that it's with MLIPs, it's very fast. It's much easier to simulate the nuclear quantum effects with the particles.
Okay.
Learning.
Yeah.
Remember, you need to speed up the process of molecular dynamics calculations.
Yeah.
Could you elaborate on how it works and what's the data set for that?
Yeah. So I stopped this.
There are any other uses of
I mean, for me, in our group, we use machine learning.
Can you repeat shortly the question? If you can.
So, well, the second part was are the different aspects of machine learning. Actually, in our group in Paris, we have at least 2 PhD students who are using, well, now remember, at least 3 PhD students who are using machine learning, but nothing to do with machine learning interaction potential. So this is trying to find, for example, correlations, some patterns that we cannot think of. So, for example, they take 100 molecules, 1,000 molecules, and then they try to find so-called descriptors, like that you can, instead of thinking of 1,000 molecules, you can see them somehow logically on one axis, like we want to do often. We have so-called reaction coordinates. That if we change this descriptor, this parameter, then there's some effect which is systematic, for example, linear or something. So they try to find the so-called descriptors that are like correlations. If we change this is probably what changes in the property of the material. And it's just very, very roughly. So this again, what people do. We do machine atomistic simulations, molecular dynamics. They just take configurations, and then it's 2 of them of our PhD students. They work in collaboration with the company. They want to improve some medicine, for example. So they want to see that if I change this and this side group in the biological molecule, would it improve some properties against some disease, for example? So this is one usage of the machine learning in our group, and many, many different aspects. Because our department traditionally, and our group, the theory group in our department, was traditionally involved in simulation of liquid properties like liquid water and so on. Our main goal is the machine learning potentials. So we have also collaborations and PhD students working on completely different aspects. Again, like finding these descriptors, correlations, which we cannot think of. There might be some physical law behind, but no one has come to find it. Maybe one sees a correlation. Okay, this property in the molecule changes this property in the properties in a medicine, for example. And then one comes to understand where does this correlation come from.
Okay, yeah. So because I also have an interesting question, I think, but it's better to discuss them.
So thanks to speaker again. It was and we stop then this.